So I mean, now we'll click the record button. There we go. Now we're good. So previously we learned the mean value theorem. And there was no, so let's see, prefix would come before. Is there such a thing as a postfix? I'm not really sure what the word would be. But there was no like word after mean value theorem. It was just called the mean value theorem. And there was no then specificity in it. We could call this the mean value theorem for derivatives, meaning the one that we previously learned. Okay, well, what was the mean value theorem? Well, it looked like as a statement the following. It was where we had, that's fun. Is where we had f of x minus f of u equals the derivative at c times x minus u. You kind of remember that at one point we saw something that kind of looks like that. This was a long time ago, because I mean, we did derivatives a very long time ago. So this was probably near the halfway point of the course, which might as well have been last year, because it feels like it was last year. So the halfway point of the course would have been around week 7, week 8, somewhere around there. We would have learned this, and that was weeks and weeks and weeks ago. You know, before all of those extremely relaxing break days that we had that helped cement our memory. So we also used this to do something. We used that to talk about what was called the VASCAR, which is where we talked about the whole idea of where if you enter onto a toll road and then you end up getting off of the toll road, you could be given a ticket. And how is it that you're given a ticket? It's that they use the mean value theorem to prove that at some point you spent. So this is what we had used it for way back then. So that may also help to kind of refresh your memory. So this was, again, what we would call the mean value theorem for derivatives. And one of the kind of restatements on this is that we could rewrite, connect the old pencil, see if that helps. I never know why it does those random lines. So we could rewrite this as f of x minus f of u over x minus u as being equal to the derivative at c, where c is some value in between x and u. So this is a restatement of the same. So this is also the mean value theorem. MVT stands for mean value theorem. Okay, well, let's now find out what is then this thing that we call the mean value theorem for integrals, because it turns out to be kind of related. So anyone still copying, or can I go to the next page? Still copying? Yep. Not a bad day, all things considering, with the rain. It's kind of nice. Pretty excited for the semester being almost over. It has felt a little long. I know I feel tired, so all of you must feel exhausted. By the way, that's not me saying I have more energy than you. I'm just saying you probably work harder than I did, just realistically. I didn't have homework. Theorem. Mean value theorem for integrals. And that's what I mean by that abbreviation, mean value theorem for integrals. So what does the theorem say? The theorem says if f is continuous on AB. Could you remind me what continuous means? That's been a long time since we've seen continuous. What does continuous mean? No holes, jumps, or breaks. Perfect. So that's a good way of thinking of that. Now, if we actually want the definition, it's for any c, c is just some constant. The limit as x goes to c of f of x equals f of c. So that's really actually what continuous means. But what that means graphically is that there are no holes or jumps or breaks. Okay, that's good to know. So if f is continuous, then there exists a number, bless you, k in AB such that f of k is equal to okay, now it almost sort of looks like I wrote the word favg, except for I think we all know favg isn't a word, so I probably didn't write that word. Okay, so that's an abbreviation for something, and it's an abbreviation for F average. Okay, which I have to tell you what that means in just a moment. Which is equal to 1 over b minus a times the integral from a to b of f of x dx. Great, cool. And now we probably need to have some way of interpreting what in the world this means. Okay, so let's see this way to interpret what this means. Okay, so we start off with some kind of a graph. And we're then going to draw an example function. Okay, so that's a perfectly good example function. And then what I'm going to do is that I'm going to say, well, I'm now going to mark this down as being a, which then allows me to put then a straight line up. And then I'm going to mark this down as being b, like so. And then what I have is that I have, let's see, can I, the opacity. I've never done that. Ooh, never done that before. Let's see if that works. Oh, yes, that actually works perfectly. Okay, so I can fill in that area that I just had there. And we, of course, know that that's what the integral means. Okay, but we could actually talk a little bit more about specifically what this right-hand side means. Okay, so when we look at this right-hand side, we know that this part right here, without that, but this part right here is an area, right? So this is some length times width, right? But only kind of just some length times width. Because it's really that we would have to take a bunch of rectangles and add them all up, and those are all length times widths. And then, well, this is now doing something right here. This is in some way, shape, or form dividing by the width. Now, what do I mean? Well, if this is length times width, or it's really height times width, it's that we would have a bunch of rectangles, and the heights of all of those rectangles would be different, but they would all have widths that would add up. But what would they add up to? They would add up to the distance from A to B, right? Because I have to have a bunch of those separate rectangles. But if I add up all of the widths of those rectangles, I get the distance from A to B. So that means that right here, when I divide by that 1 over B minus A, I'm somehow dividing by the width part that's in this computation. And so I'm left with some sort of height. Now, what kind of height am I left with? Well, it turns out that the height that I'm left with is the average height. Now, if you look at that picture, there's all kinds of heights that are available for that function. I mean, it goes up, and then it comes down, and then it goes back up again. But there is some average height of that function. And so that's what F average means, is that it's the average height of the function. Okay, but there's also something else that is true, which is that that average height happens at some particular number. Let's call it K. So at some number K, the function is at its average height. Okay, let's give an example of this. Suppose that the function that we were talking about here was talking about speed. Okay, if it was talking about speed, then if at some point if I start off going at 10 miles an hour, and then at some other time I'm going at like 150 miles per hour, but it's 70 miles per hour is my average speed. Well, sometime in between 10 and 150, I had to have hit 70, right? Because you can't just skip over that. Why? Well, because there are no holes or jumps or breaks in things like speed. So you have to have hit the middle at some point. That's what this theorem says. This theorem says if there are no holes or jumps or breaks, and you're going to try to find the area underneath the function like this, then there's some particular number that's going to tell you the average value there, the average height. Okay. So let's do an example of where we use this. So let's see an example where we use this theorem. Find the average value of F on the interval 1 to 3 and find a k so that f average equals f of k for f of x equals 1 over x squared. Great, great, great. Okay, so there are two separate parts to this question. So the first part of the question is going to have us use the mean value theorem for integrals. And the second part of the question does not require us to use that theorem. But you first have to use the mean value theorem, because the mean value theorem for integrals is telling you something. What's it telling you? It's telling you what that f average is. That's the big thing that it's telling you. It's telling you how to find the average height of the function. Let's see how. So this is a solution that we're doing. So f average is equal to 1 over b minus a times the integral from a to b of that gets old. Of f of x dx. Great, great, great. Okay, well, the a in this problem is what? What's the a? 1. And what's the b? 3. And I know what the function is. The function is 1 over x squared. Okay, so this is all stuff that we can find. So this is 1 over 3 minus 1, which I will be able to simplify, times, okay, let's, there we go. Don't know why that keeps happening. Integral of 1 over x squared dx. Great. Okay, well, that is 1/2. I think everybody will agree that that's really 1/2. Integral from 1 to 3 of, and that's really an x to the negative 2. Does that sound about right? I hope so. Well, then that means that it's 1/2 times, and now I'm going to find the antiderivative. Well, the antiderivative here is 1 over negative 2 plus 1 times x to the negative 2 plus 1. And then I have to plug in 1 and 3. One half. And then this is then negative 1. Is that about right? I hope so. And then this is x to the negative 1. And then I'm supposed to plug in 1 and 3. Well, before I plug in 1 and 3, maybe I should actually simplify that just a little bit. So that's really negative 1/2. 1 over x, and into that, I'm then going to plug in 1 and 3. So negative 1/2 times 1/3 minus minus, but that's really a plus. 1/2 times 1 over 1. Okay, well, this is the same thing then as 1/2 minus 1/3 of 1/2, which is equal to 2/3 of 1/2. which I'm fairly certain is the same thing as 1/3. Okay, so now that we found that value, that used the mean value theorem. Now, where did we use the mean value theorem for integrals? Well, it was right here, mean value theorem for integrals. It was that. That was where we used it. Okay, so that was for finding f average. And now we have the second part of the problem, which is, okay, and find a k of where the function will be equal to that. So this is where we now then say set f of k equal to 1/3. Well, that means we're setting 1/k² equal to 1/3, and then we're supposed to find what the k is. Well, by cross multiplying, 3 equals k². So can we find what k is? I hope so. It would be k is equal to positive or negative square root of 3. But now, one of those values is not going to get used. Which one of those values is not going to get used? You will not use the negative. Why not? Where are we interested in finding the value? In between what two numbers as a and b? 1 and 3. That was where we were supposed to be looking for it. So we can't use the negative square root of 3, but we can use the positive square root of 3. Is not between 1 and 3. So k is equal to the positive square root of 3, which is just the square root of 3. Done. Okay, so I think this is kind of a fun type of a problem. And this is where I would also say that this type of a problem, not as hard as some of the stuff we've done. I mean, if you look at the steps, it's like, yeah, that's pretty cool. Now, the one thing that greatly makes this much easier than other types of problems is if you're allowed to use a formula card on an exam. But what do we know that we're allowed to do? Yeah, use a formula card on an exam. So like, wow, okay, so we don't have to have this formula for the mean value theorem for integrals memorized, but we are allowed to write it down on a note card or a note page or something like that to take into the exam. Absolutely you are. And so really this is just ends up turning out to be, can you plug stuff in kind of a question. Turns out we can. So it means we can solve it. And yet, if you get to have a problem that's saying use the mean value theorem for integrals, it sounds like it's real hard, right? You're like, oh man, mean value theorem for integrals. It's supposed to be a crazy hard problem. But was it really bad? I don't think so. So this is where I would say, if I'm being completely honest about what this question would be titled as, I would refer to it as a filler problem. So when you reach the final, you will definitely be asked either a mean value theorem for derivatives or a mean value theorem for integrals problem, because I pretty much always put one of them on. And between those two problems, it's a filler, meaning it's like a break. So you're getting done with problems where you're actually doing calculations, and then you go, okay, take a little break, do a mean value theorem problem, blah, 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 blah. Then you go back to doing the normal stuff. So let's do one more question. Find F average for f of x equals x to the 1/3 on the interval 1 to 8. Okay, so turning to your closest partner and or partners, find the answer to this question, if you can, and then we'll find it together. Let's see. Enough time or not enough time? Good to see the solution? Okay, so let's solve this together. So f average is equal to 1 over b minus a times the integral from a to b of f of x dx. Well, that's equal to 1 over, well, now the b here is 8, and the a here is 1. This is then the integral from 1 to 8 of, well, the function itself is x to the 1/3 dx. So that means that I'm going to then say that this is really 1/7 integral from 1 to 8 of x to the 1/3 dx. And then I'm going to say that this is 1/7 times 1 over 1/3 plus 1 times x to the 1/3 plus 1. And then I'm going to go from 1 to 8. This is 1/7. And then I think everybody would agree that this is really then 1 over 4/3 x to the 4/3 from 1 to 8. And then if we then say, okay, well, if you have 1 over 4/3, then you'll flip it and multiply. Flip it, multiply. So it's 3/4 x to the 4/3 from 1 to 8. And then that means that that's really then 1/7 times 3/4. And then the first number that we're going to put in is 8 to the 4/3. And then we're going to subtract 1 to the 4/3. Well, the 4/3 root of 8. That means take the 1/3 root and then raise that to the 4th power. Okay, well, the 1/3 root of 8 is 2. And then 2 to the 4th power, I'm fairly certain, is 16. I mean, you could also do this with a calculator, but as we are extremely well aware, I don't carry a calculator with me. And so I'm going to say it's something like 45 over 28. And maybe even that's correct. Any questions? So we have reached a fun part of the semester of where I have now, except for the recorded lecture that will be on Friday, I have now finished all new material. So again, there's some new material included on Friday. But in terms of anything that is brand new, as opposed to just kind of bringing together the stuff that we've done, we finished. And so then we say, okay, well, what are we going to do with the rest of our time? Clearly party, but probably not. We're going to review for the final. So here's then the plan. So tomorrow is a WebAssign day, as we know. And then Friday then, recorded lecture of where we're going to do, and by we, I really mean me on video, and then all of you watching it. We're going to do some shell method problems, some additional ones. I think I do 2 problems or something like that. Then Monday, we're back normal live in person or on Zoom if you're on Zoom. We're back to normal live in person class. What are we going to start doing? We're going to start going through the practice final. We're going to start doing the questions. Now, one of the class periods next week, I plan then on having the where it's going to be one additional web assign. We don't actually have any new assigned web assigns, but I'm going to do one more in case you didn't finish up anything. Okay, so that'll give you an opportunity then to ask me questions for anything that you haven't resolved yet. But other than that, it's going to be review. So that will be Monday. I don't know which day we'll do the web assign, but like between Monday and probably Wednesday and Friday, those will be review days. And then the following Monday as well, also a review. And then I think it's between the two sections, it's Tuesday and Thursday, and I don't remember which one's which. I think this class is Tuesday. No, this class is Thursday. Okay, so switched it in my head. So is then the final then for next week, or not next week, the week after that. So 2 weeks from now. There we go. So that's our game plan. Now, to make this final review as useful as possible, here's what I would suggest. Try to work on the problems. Realize that I'm going to be going in order. Okay, or at least I'm going to try to go in order. So that means that gives you then a pacing of, cool, let me try to, over the weekend, look at, the first couple sections. Because if you come to the review session and you're watching me do it, then it will not be a review for you. It'll be like watching a television show. And it won't be very meaningful to you. So try to have worked on it ahead of time. The final is cumulative, so we're going to try to review pretty much the entire course. Now, I on purpose plan my course out so that I have all of these days for review, because leaving the course with a general knowledge is a kind of big deal for me. I want you to kind of catch what this course was about. Now, not because I want everybody in the world to be, super calculus buffs, but rather I want you to get the intention of the course. If you didn't ever hear it before, I will tell you now the intention for why everybody takes calculus. It's not really to learn calculus. I'm not sure if you are aware of this. Really, the only people who have to learn calculus are people who are math majors, because then you will actually use calculus for a living. For everybody else, the point of why you're taking this is for you to gain a general ability at using logic and solving problems. That's why you take calculus. And then you go, that doesn't sound fair. Yeah, okay, but that's what's been done since antiquity. So this is like a 2,000-year-old problem, which it turns out math is the very best way of having people learn problem solving. Because the only other way is to lock people in rooms for those, whatever they're called, breakout rooms, and then go solve it. But I think that's called kidnapping. So we can't do that. So instead, we lock people in the little box that's called math, and we tell them to get out. And so that's then the problem solving that we do. That's really why most people have to take math, just to learn problem solving. Unless you're in some of the subjects where you'll have to then use the math in your courses, which if you're a scientist, you will have to use it in your courses. But why are you using it in your courses? Ultimately, it's because you want to do something else. It's not probably because you want to do the math. Okay, so that's our game plan. And if you have any questions, please feel free to email me or stop by the Math Enrichment Center tomorrow, or come to class tomorrow. So, have a good one.